Hello everyone. We are doing a bit of a different video today because the NOI just took place on Saturday, and I did a quick check and realized that it seems that nobody actually reviews the NOI problems on well, any publicly accessible channel, right? I'm sure that some of your school teachers may share solutions, some of your seniors may share solutions, but it's not publicly accessible. And some of you may know that actually I am also a past NOI trainer. I used to conduct classes at ACS. And although I haven't been doing it for a while, I do like to look at NOI problems when they come up. I think they are pretty fun. And so for those of you who are just math Olympiad means you have never looked at the NOI before, I think this is a good chance to just take a look and have someone who is still using math language to talk through NOI problems and also to draw some connections to math problems. And of course, for those of you who are actually fully in the NOI boat or other CP and coding competitions, hey, likewise, I'm going to draw some analogs to Math Olympiads. And so, in so doing, maybe I'm going to make both the Singapore Math Society as well as whoever is in charge of the NOI, I forgot their initials, pretty happy because I'm sure they want more participants. So, for those of you who are familiar with the NOI, feel free to skip past the next 2 or 3 minutes where I talk about the NOI format. For the rest of you who are less familiar with it, let's just talk about the difference compared to the SMO. So the NOI has 2 rounds, the preliminary round and the final round. The preliminary round just took place on Saturday. The finals will be in a few weeks' time. So both rounds are 5 problems in 5 hours worth 100 marks each. Now this is a lot of time. This is longer than literally the IMO, the SMO round 1 and round 2. So why does it take so long? Well, basically when we talk about NOI problems, you are writing code, which means that you are doing 2 things in solving these problems, right? You are actually sort of figuring out and then coding it out. Now, for those of you who are not familiar with coding, what I'm going to do later is I'm not going to do any coding. I am going to talk about the figuring it out process, and I believe you can understand that too. The code it out part, obviously you will need to know a programming language, which is primarily C++ for our NOI and IOI track. You don't need that for understanding this video. Okay, now the NOI is not hand graded, it is auto graded. How it works is that there will be a task. The person who sets the questions will also generate a bunch of test cases that you don't get to see. And if your code is correct, when you feed the test case into your code, it should output the correct answer within a time limit. So that means that you can get 100 marks if you pass all the test cases. And also there are subtasks which are easier versions of the question, which if your code can at least pass the test cases in the easier cases, you will get partial marks which are explicitly stated. This is like the SMO round 2 where you can get partial credit, but the difference is that they don't tell you in the SMO, oh, if you do this, I'll give you 3 marks. If you do this, I'll give you 5 marks. They don't tell you that, but for the NOI, it tells you explicitly how many marks the subtasks are worth. Now, awards and scoring wise, for this year, there is a new cutoff score to get into the finals. And it's not announced in advance, but it was just announced less than 24 hours before this video that the cutoff was 200 marks. So that means 2 out of 5 questions fully done would allow you to qualify for finals. If you are also in the top 5 in your school. The NOI has this additional rule just because there is a little bit of logistics constraints. If you were to get into finals and you go to NUS School of Computing, they do not have infinitely many laptop terminals for you to code on. So only 5 per school plus 1 for female contestants who do the best but may not be in the top 5. So that means for if you're in a girls' school, you automatically will be the top 6 who get at least 200 marks will get in. If you're in a boys' school, it will be the top 5. And if you're in a co-ed school, then there's sort of one extra reserve space for a female contestant who is not in the top 5. The top 5 in a school is such that those of you who are in a so-called more chill school where not many people are taking part, you have an advantage perhaps for the first time in the world of Olympiads. If nobody in your school cares about Olympiads, but your school takes part in NOI, you have a much better chance of getting into finals. And this is important because unlike the SMO, the gold, silver, and bronze awards are only for those who qualify for finals and only based on the finals scores. So it is not the same as SMO where you add up the scores together and those who miss it by a little bit get a silver or bronze. No such thing. There's a lot more to say, of course, but I'm not here to do a briefing on the NOI. You can refer to the website if you want to take a look. For the remainder of it, we are now going to look at the NOI problems, and I will also mention some SMO or Math Olympiad problems in parallel as a little bit of a comparison. Okay, so the first that we're going to see is task number 1. There are 5 tasks as they are called for NOI. We are not going to look at task number 5, by the way. That is too hard for the purpose of this video. So if anyone would like to share their solution for task number 5 in the comments, feel free to do so. Otherwise, let's look at task number 1. Now, task number 1 traditionally for the NOI is sort of just a giveaway problem, meaning that anyone who has some basic coding knowledge will be able to get it right. And so if you were to read this problem, from a math perspective, it is actually a bit silly, right? So it says that Ziv has n pairs of sticks numbered 1 to n. The ith pair contains 2 sticks each of length ai. So we know that in math we would use a sub I, right? In coding, these are basically an array or a list of numbers, so they are using square brackets, but you can think of it as just a list of n numbers, which is what the document will tell you the format, right? There are n lines of input, each containing 1 integer. So the ith of these lines contains ai. So you are given n as well as the whole list, and you want to pick 2 different indices to form a rectangle with the largest area. This is pretty silly, right? It's pretty silly because obviously you just pick the 2 biggest ones. And so indeed, there's no catch. If you were to look at the test cases, these are just given to you so that you can make sure that you don't misunderstand the problem. It is really as easy as it sounds, right? If you have 8 and 9, output 72. If you have got 16, 44, and 18, you output the biggest one, which will be 44 times 18, the 2 bigger ones. And then in this example of a long list, they can repeat, but you still can use 99 times 99. So this is very easy to understand. This is the type of problem where essentially if you know how to code, there shouldn't be a challenge at all. We have got a fair share of these in the SMO as well. I've just, for the sake of having a nice parallel, just picked a random problem from the SMO Junior, which is something like that, where as long as you've done any Olympiads before, you look at this, you're like, I don't see any problem with this. I know how to add up things in an arithmetic sequence. Just use the so-called Gauss method, get the number of terms, get the average, and yeah, just do that and you are fine. If you have never seen Olympiads before for math, this is going to look a little bit intimidating, but once you have seen any Olympiad before, this is easy. Now, the same applies for those of you who are seeing the NOI for the first time. You would be wondering, why is the problem statement just now 3 pages long? But if you have done any coding before and you have seen the NOI format, you know that there is really nothing to worry about. Right? So without any further procrastinating, we shall move on and look at the more interesting problems, beginning with problem number 2. Task number 2 is called Hungry Cats. It's always a funny little story. This here talks about cats that are eating each other. There are n cats numbered 1 to n. They each have a happiness level, and at any point in time, a cat can eat a less happy cat. After that, it will increase its happiness level by 1, but it can no longer eat any other cats, and the cat that has been eaten obviously is no longer there, it has been eaten. So the question is it possible for only one cat to be left at the end and therefore all other cats were eaten? Okay, the input tells us that we have got all of the information. They tell you all of the happiness levels. You're just supposed to output yes or no. And we are told that there are up to 200,000 cats, and the happiness is between 0 and 1 billion. Now, for any of these NOI problems, they will tell you the constraints, because when you want to solve this problem, your code needs to run quickly enough, not just that your code works eventually. Now, generally, we can take as a benchmark that depending on how you count, the time limit allows you to have up to 150 to 200 million operations, where this means that, for example, if you are going to try every possible permutation and do something that takes n factorial possibilities, that obviously will fail, because 200,000 factorial is hopelessly big. Now, you're also given a lot of ways to get partial marks. For example, if I told you the n is 2, that just means there's 2 cats, and we should have no problem telling whether it's possible. If there are n at most 3, we should have no problem telling it's possible. If let's say that we are told that there is this list of them being non-decreasing, maybe that would be easier than the general problem, which is no additional constraints. Okay, so anyway, your task is always that, am I able to do it? Just answer yes or no, and your solution cannot be too inefficient. Now, we do like to use the sample cases as well for intuition. So if this is 2, one is much bigger than the other, the answer is yes. For this one, which is 3, the 3 of them are pretty far apart. So you can do it by letting the second eat the first, the third eat that second one. That's clearly possible. And then the third example given is that this is impossible. 10, 0, 24, 25, 10. The fourth example is that this is impossible. 2, 25, 11, 5, 20, 26. And although I don't 100% know how to test all the possibilities in my head, I kind of see what the issue is, which is that there are either repeats or there are 2 of them that are pretty close to each other. Now, unlike the SMO, where you don't get any hints, and your partial credit came from you, the subtasks are also, in a way, hints. So it sort of tells you things to look out for. So for example, if one of the subtasks is that h1 equals to hn, why is it that this is only worth 6 points is in itself also a hint. And if you think about it, it should be quite easy to guess that maybe it's just the answer is no. If 2 of them are the same, maybe it is not possible. Now, we can explore that also alongside this statement that, oh, it is useful if they were in order. So this is sort of giving you a hint that you do want to sort them. Of course, when we say sort them, in code, we know that there's just literally just use the function sort, right? So sort them and then do something, and what to do is what we need to consider. So let's switch over to the Microsoft Word tab, and what we are going to try to do is to explore what sorts of cases work and what sort of them don't. Now, I've entitled this Simplifying the Illusion of Choice because we don't actually have that many ways of doing this. So let's say that I were to just put a bunch of numbers in order that are really far apart. Let's say like this. Now, it is not very difficult to see that I could just have this eats this, now it's 5, this eats this, now it becomes 8, this eats this, it becomes 101, this eats this, it becomes 1001, and then we succeed. So there is no apparent problem with this approach once you have sorted them. Let's also think about what happens if they were closer together. So if let's say that they were 2 apart, it's still okay, right? Because if they're 2 apart, the same strategy is still fine because after it increases by 1, it still doesn't hit the next value. So the same thing can still work. So how about if they are 1 apart? Let's say 1, 2, 3, 4, 5. Now, if you have 1, 2, 3, 4, 5, I can say that if I do this, 2 is 1, it now becomes 3. Oh, okay, so 3 cannot deal with 3. But I say, never mind, I can use the 4 to eat the 3 and it becomes 5. But now I've got 2 5s, right? And so how am I going to ever get rid of the 5? You might say, never mind, I have the 5 here. Well, the 5 here can eat the 3, but after it has done that, it has been used up. Then you realize that, hang on a second, this is not even about their size, right? The issue here is not even the size. The issue here is that both of these have already eaten a cat, for want of a better expression. They have been used up. So how do I make sure that I have got enough vacancies? Well, I realized that, okay, in this process, if there's 5 cats, it means that you must eat 4 times. The cat that has the least happiness, the smallest number, can't ever eat anything. So you know that it must be the all but the lowest one must do the eating. Now, if all but the lowest must do the eating, then we would say that. So obviously, if all but the lowest must do the eating, then the second lowest must eat the lowest, because what else could it eat? And then the third lowest must eat the second lowest, because what else could it eat? And moreover, we cannot say just do this. It must be in order, because if let's say that your first move is to eat away this guy, then you have used up that cat by eating it away, which is also not okay. Therefore, we can conclude that they must be done in order. And so if you have sorted them, it must be that they just sequentially eat from smallest to largest. Therefore, the condition is going to be that A2 must be more than A1, but for all the rest, A3 must be more than A2 plus 1 because it has already eaten. A4 must be more than A3 plus 1 and so on. In other words, what we are saying is that this gap can be at least 1, but all the remaining gaps must be of size at least 2. Now, this is basically already what it means to solve the question for the NOI, because writing this out in code is very simple. You just sort them, and then you just do a single loop to check all of these are true. Now, I feel a little bit wistful in the sense that if the cutoff score is 200 points, it means that doing questions 1 and 2 is enough already, of course, plus being the top 5 of your school. But if the cutoff is 200 points, it means these 2 questions are enough. I can see that some schools have less than 5 qualifiers. I'm not sure if it's because it has fewer than 5 participants. But I will say that it's kind of a waste if you are not able to, in 5 hours, to do 2 questions. And that's mainly because maybe you are recognizing the NOI as a coding contest. I will say that it is an Olympiad. An Olympiad for math and an Olympiad for informatics are similar in the sense that you are trying to do things a bit more creatively. So this is something where you don't need to know any special data structures, algorithms, any graph theory, dynamic programming. If none of those sound familiar to you, you don't need it. You just need to put them into array, sort it, and write one loop. Almost invariably, the NOI will have one problem like that, which is almost a logic problem where the code is easy. SMO also has plenty of these questions where you don't need to do any sort of solution bashing or high-powered theorems. It looks like as if there's a lot of choices, there's a lot of things, but it really is just common sense. So, tip for future reference is that do take a while to just think about whether the question is obvious from an intuitive perspective. Right? Do not run in and sort of straight away start thinking of which data structure is going to solve the problem. Okay, so let's now look at task number 3. This is on airplanes, and the statement has gotten longer. Part of the skill required is to be able to tell what matters, a bit of reading comprehension. So I'm going to condense it for you. So you have basically got a grid which has H rows and W columns. And we have indexed them ij for the row number and column number. We now have a bunch of passengers. Each passenger has a preferred column, but apparently not a preferred row. So no 2 passengers can occupy the same seat. And there is this requirement that a passenger in an earlier row must not be seated in a later column. So it means that if you have, let's say, 1, 5. Row 1, column 5. And the next one is in row number 2. You cannot have row 2, column 3. You can have row 2, column 5 is okay. You can have row 2, column 10. That is okay. Now, the gross passenger satisfaction is defined as the minimum Manhattan distance between all pairs of assigned seats. The Manhattan distance is defined as this, which is basically how many rows plus how many columns apart they are. So you have to determine what is the maximum possible satisfaction. So basically you want to space them apart, right? You want them to be spaced apart, and the metric we're using is this Manhattan distance, and we're trying to make the one that are the closest together as far away as possible. In other words, this is just social distancing. So find the maximum or determine that there is no valid assignment. And as usual, we're given all the inputs. We are told that the dimensions can be up to 10 to the 9 by 10 to the 9. Wow. But there are only up to 200,000 passengers. This is just saying they will give you the columns that are meaningful columns, right? So they will be within the width. Okay, so now we can look also at some of the test cases alongside the subtasks and what constraints they have. So the first one, remember what they give you is the height and the width. The first example is that if you have a 5 by 1, and all of them want to be in column 1, but there are 6 of them that want to be in column 1, for a 5 by 1, obviously that is not possible because there's not enough space. For the second case, you have got 2 by 7, and they want to be in columns 1, 2, and 3. So if it's a 2 by 7, but they want to be in columns 1, 2, and 3, then in reality, it doesn't actually matter that much. They are going to just be in column 1, column 2, and column 3. You know that 2 of them will need to be next to each other in the same row. So that's why if they are in the same row next to each other, then their Manhattan distance is 1. So this is the minimum that you can, so the maximum that you can get in terms of spacing. But if let's say that now you have got a 3 by 7 and they are in 1, 4, and 7, it means that you can put them into row 1, column 1, and then after that, row 2, column 4, row 3, column 7. So that's how you end up with a distance of 4. Okay, so the first pass through the test cases is always useful for us to understand what is the question really saying. Did I understand it right? And sometimes they're kind of nice. They actually give you more detail. So here, you see that 1, 1, 11, 7, 3. So it means that the passengers, 2 of them want to be in column 1, 1 in column 3, 1 in column 7, 1 in column 11, and it's in a 4 by 11 as we can see here. So this is an example where it is valid. And you can see that here is the minimum distance, which is 2, right? These 2 passengers are 2 steps apart by Manhattan distance. Whereas this is not allowed because they will be earlier row, later column. Basically, you cannot have this northeast to southwest direction between any 2. That also means that not only is this violating it, this one and this one would also be a violation. This and this would also be a violation. There are quite a lot of violations in this example. Okay, so let's come back and try to write out some of these test cases and understand a bit better how they work. But before that, I'm also going to take some hints from the subtasks. Okay. So Width is 1 is just saying that if any of them, well, all of them will need to tell you that they want column 1. So can they all fit? It's just space them out as much as you can. Then the next one is they are each asking for the ith column for passenger I. And then there's also this further arithmetic sequence condition. I think that is also kind of intuitively clear that you just want to sort of space them out like in a straight line as much as you can. Now, the rest of them are basically just going to be that if your solution is very inefficient brute force, that's why it stops at 8, and then this one stops at 3000, but this one goes up to 10 to the power of 9. Okay, so let's try to understand this, and I'm going to call the approach basically for now just systematic guessing, and we'll mention the algorithm in a little bit. Right, so let's say that I draw out an example. Now, a very useful thing to do for both math and for CP problems is that you want to come up with a simple but not stupid example. Right, so it needs to be sort of like interesting enough that you need to think a little, but not so difficult that even after you tried out, you have no idea whether your answer for the small example is correct. If you don't know whether your example is correct, then you don't know whether you have drawn the correct conclusion. Right, so I'm going to sort of draw something that is not too scary. I'll just put a 3 by 5. And we're going to just think through some examples. Right, so let's say that now I have got 1, 2, and 4. Now, column 1, column 2, and column 4, I call it systematic guessing because a lot of this is going to be not something that you have to prove, but it's just common sense says that, okay, I should probably put the person in the first column first. Now, because I know that this is not allowed and this is allowed, obviously I'm not going to put the person down here straight away, because when I put the person down here, then it basically forces everyone to be in this back row, which may not be that good. In fact, I can always just assume that I push them all forward. If you're all in the back row, just like any teacher will say, hey, come forward, there is so much space. So we should put the first person into the first row. Now, then what I can do is say that, okay, if I'll put them next to each other, the distance is 1. That feels pretty lousy. I think I can do better, right? So maybe I put them here, and so the distance is 2. Manhattan distance, remember, 1 plus 1. And so the distance is 2. If I put them here, the third passenger, it will be the distance is 2 again. If I put the passenger here, the distance will be 3. But that makes no difference to me, right? Because I'm looking at the smallest distance, which is 2. So can I do better than this? It doesn't look like it, right? Because if I want to do better, it means that I want to make the distance 3. I need to put the passenger here, and then where do I put the third person? They cannot go any further forward, they cannot go any further back. So therefore, in my case here, a 3 by 5 with 1, 2, and 4, it should be 2. Now, what did I learn from this process? I learned that the first person should always go into, the first person means the person in the leftmost column should also go into the first row. I also learned that every time when I was looking at the Manhattan distance, there was kind of no point in like checking the one between row 1 and row 4, right? I didn't check the distance between these two, because obviously the distance between these two will be more than the distance between these two and the distance between these two. So I realized that I only need to check just so-called neighbors. There is no good reason why I need to check those that are very far apart. The math teacher in me would want to say that this is also an instance of the triangle inequality. The triangle inequality works both for normal distance and Manhattan distance. Now, another thing that I realized from this example is that I don't actually have a very meaningful definition of space them evenly. Because in this case here, yes, this will give me 2, so will this, right? And so will this. So there are many ways that it can be done, and I'm not 100% sure that evenly spaced is actually the best way to go. So here's, I guess, my other concern. My other concern is, before we make any further deductions, does it affect if I've got multiple in the same column? So if let's say that I have got now 1, 1, 2, 4. Now if it's 1, 1, 2, 4, and I want to do better than the distance being 1, I need to do this. But okay, so if I did these two apart, then immediately I know that the person in the second row is actually going to be restricted by this guy to be here, and the distance is only 1. Okay, so seeing as that is the case, maybe we should say that I'll pick another example, like instead of 1, 1, 2, 4, how about just 1, 1, 4. In this case here, this would be optimal. It's quite easy to see that. Also, I kind of can tell that my strategy didn't really change that much, right? It's just that instead of now where do I put them in the next row, sorry, the next column, it's just where do I put them in the same column before I move on. Now, with all of this being said, you would also realize that I mentioned a lot about the answer each time, right? Which is that, okay, if I can do 1, that's quite bad. Can I do 2? And so when I say, was I able to do 2, I say that, all right, let me put them 2 apart and see whether the rest can go in. Now, we realize that actually, if I have given a target score, it's easy to track. So if I have a target score, I can see whether that target is attainable by just using a greedy algorithm. Now, a greedy algorithm just means that pick the first thing that works, and it is not difficult to see that in this case, the first thing that works is the best choice. So if let's say that I had my 1, 2, and 4, I say that, can I get 1? Well, obviously you can get 1, just do this. Can I get 2? I say, all right, this can come here, and then after that, this can go here. Now, this means that if I went 1, 2, 4, 5, I can continue on and say that 2 is attainable. Remember that because of the rule, I only need to keep going downwards. So it's pretty easy to know what's the best choice, right? Like, if let's say that I went down to here instead on my first turn, then I've wasted some space if my target is 2. On the other hand, if my target is 3, then I can say that, all right, my target was 3, but look here, this was 3, and then now if I want to go to here, the maximum I can get is 2. There is not enough space to get to 3, and so therefore that doesn't work. Okay, so with this thing now in place, we will use a very common strategy when it is quite easy to use the target to check whether something is possible. Then we can ask ourselves, does it always mean that a lower target is easier to get? And the answer is yes, right? If I can get 5, I can get 4. If I can get 4, I can get 3. It is true that a higher target is always more difficult, a lower target is always easier. Now, this allows me to say that whenever an easier target is if and only if you have a smaller number, I can binary search the answer. BSTA is short for binary search the answer, and what that means is that you basically are going to play a higher or lower game, right, on your range of possibilities. Now, the nice thing about binary search the answer from an efficiency standpoint is that if your answers can go up to 1 million, you are still only going to need to check up to log base 2 of that, which means about 20 times. In this case, it goes up to 1 billion, that's still okay. And so you can binary search the answer. Basically, it means that your range is from 1 to 1 billion, means that the maximum Manhattan distance is going to technically be 2 billion minus 2, but nobody cares about that. So it's just the range is from 0 to 2 billion. The range is from 0 to 2 billion, which means that you are just going to test a target score k. For each target score, you're basically going to have, okay, so first thing I should actually is sort out the list of columns. Right, so sort the columns. Then after that, your k is in the range from 0 to 2 billion. You test the target score, so you will start with the halfway point, which is 1 billion. And then you will go and say that for each test, what it entails is to put the passenger in the smallest row that will make the Manhattan distance at least k. And it doesn't matter whether they're in the same column or not. If you are able to make this happen, then great. So just try doing this till the end. If you ran out of rows, meaning that it's not possible, then your target has to be lower than k. And if you succeeded, then your target is k or more. And so your binary search means you're chopping it half each time. And of course, we say 2 billion is the maximum, but in reality, you can just use height plus width. Which, but if you did it up to 2 billion, it will also be technically fine, just that it would be up to you in terms of how you are going to code it out. Now, Implementation notes, for those of you who are trying to code this, that I think there are a couple of things that you may need to watch out for depending on how your code works. Now, of course, I'm assuming your binary search is correct. So first of all, make sure that you don't have any overflow because it's 2 billion. We know that your integer limits are basically going to be around there. So use long longs if you need to. The second is also make sure that there is a way to detect that it is impossible entirely, which will basically be when there are too many people in the same column. That's the only way it can happen, right? So there are more people than rows in a column. And yeah, pretty much that is going to be it. This is something that if you are looking at it from a perspective of math problems, it also actually is surprisingly common that you have something like this. Now let me just grab a math problem. So a lot of these are ideas that will work both in the world of math as well as in the world of coding, except that what's a reasonable size will be a bit different. So this is from the SMO Open 2023. If you were to look at this problem on monkeys picking up peanuts, I will say that this would be a human example of binary searching the answer. Meaning that if you have got 200 monkeys to pick up 3,000 peanuts, and you want to know whether it is possible to find the maximum number of repeats that are guaranteed. You basically ask yourself, okay, why is it that the question asks you for the maximum number of repeats that are guaranteed? Is because there cannot be no repeats. If there's no repeats, then the number of peanuts that would be picked up is at least going to be 1 plus 2 plus 3 until 100, until 200. Actually, it should be 0 until 199. But the point is that that's much more than 3,000. So therefore, something must repeat. Now, if let's say that we ask ourselves, must there be 100 repeats? Now, obviously the answer is no. There is no reason why 100 of them need to repeat. So you then can basically binary search the answer to test in between. Am I able to make it have, let's say, 20 repeats? Am I able to have 10 repeats? And just higher or lower? Because if you are guaranteed to have 2 repeats, you are also guaranteed to have 10 repeats. If you are guaranteed to have if you're guaranteed to have 10 repeats, you're also guaranteed to have 2 repeats. So a bigger number is always going to be harder than a smaller number, just like what we've just seen. And therefore, you will do it, except that you are doing it humanly, which is why the numbers are 200 and 3,000 instead of 1 billion and 200,000 passengers. Okay, so that is task number 3. The last one that we're going to look in this video is task number 4, which is on digits. Now, this is almost like sort of goading you into thinking that it's a math problem, but as it turns out, it really isn't. Just because it says that Jaden is a math nerd, that does not mean that you are supposed to use a lot of math. So the problem is supposed to be that you have a m-digit string x, which is his favorite number. He's given a bunch of other m-digit strings. Now, it's kind of important for us to quickly check, right? So M is at most 5, N is at most 200,000, K are the digits, so it's just the digits are from 0 to 9, right? At most. But let's just see. So there are up to 200,000 other numbers, but they are only 5-digit numbers. Now, of course, we know that 5-digit numbers, there aren't even 200,000 of them, right? So this 200,000 is sort of just there to scare you. Okay, now this is a little complicated for tracing out, but basically the idea in the problem is that Jaden wants to know what is the minimum cost needed to turn the bunch of new numbers into his favorite number. His transformations are going to be as follows. Take a range, so L and R for left and right. Take a range, and for everything in the range, increment it by this A's, where A's are a bunch of given numbers. And it will be done mod K digit wise, meaning that actually you are not adding a number, you are just adding something mod K so that all the digits still make sense. Now there's also a cost involved, and the cost is also given to you. If it's impossible, I'll put -1 instead. Okay, so let's look at an example. Okay, so in this example here, his favorite number is 676. He's going to have 6 numbers that are 3-digit numbers. All the digits are less than 8, which means that the operations on adding the digits are also done mod 8. Okay, now what are these list of things? Remember that there were 2 lists of numbers. The list of numbers were the A's and the C's. The A's are the things he's allowed to add, and the C's are the cost. So if he does it from L to R, his cost would be CL plus CR. So he's allowed to basically just add 1 to the first digit. It's the only thing he ever adds. Add 2 to the second digit, add 3 to the third digit, mod 8, and then the cost will be based on these. Okay, so there's quite a lengthy explanation of this test case, so I think we can use that. So if he starts from 356, what he is allowed to do to make it become 676 is to use the +1 on the first digit, +2 on the second digit, and +3 on the last digit. So the operations he uses are +1 +2, and then +1, and then +1. The costs were based on the table: 3 plus 1, 3 plus 3, and again 3 plus 3, right? Which is based on the first operation is adjust the first 2, the next operation is just adjust the first one. Okay, so then there are more examples of how it can be done. Let's say that if it's already the number itself, then the cost is 0, you don't have to do anything. If the number is this, then maybe you can't reach it at all, so you output -1 to say that it's impossible. Okay, so this is how the problem is presented. Now, I find that personally, it is pretty interesting to ask Math Olympiad students to try to do these kinds of problems for the first time, because my experience is that I want to try to solve for a good strategy, which is obviously what we are supposed to do, but sometimes we are sort of misunderstanding what is the meaning of the word solve. You see, when we talk about solving for Olympiad math, we are a human and therefore we have limits. When we talk about solving for informatics, for coding, the computer has its limits, but they are very different from ours, which means that the computer can do a lot more brute force than us. And that is actually what happens when you ask AI to, let's say, solve the AIME. I tried entering the AIME problems into ChatGPT. It can solve most of them, but for a lot of them, what it did was just brute force code. So do you consider that solving it? It's doing it in a different way from what a human is supposed to do, because its code basically considered 100 million possibilities, whereas that's obviously not what you're supposed to do. So conversely, we are supposed to be willing to consider the 100 million possibilities in code and not just try to strategize a solution out. So here's what the solution for this problem can roughly be. Now, it is quite significantly motivated by the fact that n is huge. The number of things that I have to answer is a lot. But m is quite small, meaning there are 5-digit numbers. Now, if there are 5-digit numbers, what that means is that this is not very hard, because it's nowhere near 200,000. Even if they were all the 5-digit numbers, that's going to be just 90,000 of them, not 200,000. Now, it's very funny whenever we say only, right? Because 90,000 is not a human thing you want to do, but 90,000 instead of 200,000 is a very big difference from problem solving perspective given the computational resources. Now, that means that also all of them, I am trying to say, okay, I've got, let's say, my target number X. I'm trying to get from all this bunch of things to try to get to X. But most of them are going to overlap, right? So if let's say that I got to here, from here to here in one step, let's say the number 1, 2, 3, I got to 2, 3, 4 in one step, then getting from 2, 3, 4 to X and getting from 1, 2, 3 to X, I shouldn't have to redo it from scratch. Now, this is essentially already hinting at it being a graph problem. This is basically a graph problem. And this is a graph problem where here are the things that we need to do. Firstly, state what are the vertices. Now, the vertices are basically all the m-digit numbers. Secondly, what are the edges? Now, the edges are going to just be the things in your array, the list of A's that tell you what you can do to each of them. But basically, it's allowed transitions. And also, the weights are going to be the cost. So in a graph, we can have a weighted graph or an unweighted graph, right? So I can put weights on my graph. What I'm just curious about is whether this is going to be feasible, because if I want to get from everything to here, I can just reverse them and start to go from X to everything else and pre-compute it instead. So instead of going from things to X, I can go from X to other stuff. And the whole thing therefore just becomes a single instance of Dijkstra. Your single source shortest path is sufficient. Now, we just want to check before we start coding whether this is actually solved. Meaning that are we in that vicinity of a few 100 million operations, or have we completely exploded it? Now, this is where you need to know your complexity for classic algorithms, which includes your Dijkstra. What we need to do is to know the complexity as well as to know the number of vertices and edges in our graph. So your Dijkstra complexity, if you were to code it in a normal way, can be said to be just order of E log V, right? The number of vertices is, as we have said, pretty small. It's at most 90,000 if your V is using 5-digit numbers. It could be fewer digit numbers. It could be that your K is less than 10, such that your digits are in base K, giving you, let's say, just like a few thousand numbers, but that's even better. Now, we talked also about allowed transitions. So each vertex, your number of choices, let's say if you have a 5-digit number, you can go from basically any start to any end, which is only going to be 15 possibilities, right? So 5 choose 2 is 10 ways to have a different range, and 5 ways to just pick one particular digit. So each vertex has degree at most 15, which means that your graph has at most that 90,000 times 15 over 2, which is basically less than 100,000 edges. Sorry, less than 1 million edges, I should say. Comfortably less. And so if you have less than 1 million edges and this thing is a small number, I think we are very safely within the few 100 million. Now, all that is left for you is to do the coding carefully. So that now depends on your implementation understanding of Dijkstra's algorithm. How are you going to pre-compute everything, store it so that what you're going to do is to calculate all of the shortest distances at one go, store it into some array, and then after that, when you have the queries, you can just output them instantly. So you're pre-computing all of this. This is in total not per query. Now, in this case here, I didn't really look at the subtask just in order to make the video not too long. Of course, you would be able to have looked at the subtask in order to find some partials that could have been done in some of the special cases, including, let's say, when you only have 1-digit numbers, or if you only have 2-digit numbers, or if your digits are just 0 and 1. Now, this is just a quick, almost like introduction, come review. It is not very rigorous. For these few questions, if you want to ask anything, feel free to do so. This is a bit neither here nor there in terms of, is it for experienced coders or is it for people who are new or people who do not know anything at all about the NOI. But what I will say is that we can actually understand the logic, just that the final thing to do is often going to be so-called a canned algorithm, like let's say Dijkstra, or let's say binary search the answer plus greedy. This nomenclature will take a while for you to get familiar with. Okay, so let me know if you want more videos on NOIs. I am not going to show it in terms of code because there are definitely better coders out there, but in terms of the thought process, I just thought I'll share some of the similarities and also some of the ideas that can be used on NOI problems. Okay, so thanks for watching. Bye-bye for now, and all the best if you are taking NOI finals pretty soon.